I sort of envisioned this app because of just some personal history. So I'd gotten myself up to around 400 pounds and got into a bit of trouble, just back troubles and stuff like that. So my mobility wasn't too good. And previously I'd always lost weight from doing exercise, and I made a lot of exercise. I would exercise hours and hours a day, and wasn't used to doing any sort of dieting or managing my diet at all. But through consultations through doctors and stuff like that, doctors had put me on this ketogenic or keto diet, it's called now. It's essentially a low-carb diet. And the phases that I was going through for this diet put me at essentially less than 5 carbs a day to keep me in ketosis. Unfortunately, you have to be very careful when you're on these types of diets, and I ended up in the hospital due to bad diet choices. Apparently, you can't live on steak and romaine lettuce. So I ended up in the hospital. The doctors say my heart stopped for about a minute. The cause of that was low potassium. So this is really where a lot of this is coming from, and my realization that you could lose weight by controlling your diet and without exercise. Calories don't necessarily matter, and I can vouch for this because I don't count calories at all, but I've lost about 180 pounds now. What really matters is the macronutrients in food and how they're balanced out. So I eat a fairly high significant protein diet, lots of fats, and still keep my carbs quite low. But I don't continue on ketosis diet or go into ketosis. I do recommend, if anybody's sort of having weight loss issues or having diet problems or doing that whole thing, you're not sure what diets to choose, is try a keto diet for a couple weeks. I don't recommend long term. Ideally under a doctor's supervision, and just sort of monitor yourself. The other danger I found is that not everybody, they have those ketosis strips that you can use to sort of test yourself. Those don't work on everybody, and I had never realized that. I didn't realize that until going through a doctor. So for instance, for me to sort of be able to determine if I'm on ketosis, I have to essentially go to a doctor and get a blood test. So really, it's best under a doctor's supervision if you're going to go hardcore ketosis. Okay, so I envision an no-eat app that uses deep learning to categorize foods, deep reinforcement learning to track food intake and monitor and manage that, and essentially deep reinforcement learning to sort of decide what foods you could or couldn't eat. Okay, just some disclaimers. I didn't use this app to lose the weight. Like I said, I've got a pretty static diet now. I keep my food intake pretty controlled. I might deviate from a little bit by changing foods and stuff like that, but mostly, most of my diet is pretty static. I might go out of bounds, but I pretty much know the macronutrients of the foods that I need to consume to be right on track in my diet anyways, and I'll stick within those. So that includes, not eating pizza or bread or pasta or stuff like that. But I mean, that's just my choice. And the implementation of this app was really about teaching concepts. In my next book is sort of the final project, is sort of pushing everything together. So it was sort of broken up for that purpose. I sort of broke it up into a classification, transfer learning piece, and some other pieces. I'll go through the architecture in here in a second. It was really to show that, but what I found is that it was actually a really good way of optimizing reinforcement learning problems, because reinforcement learning problems are very notoriously take a long time to train. They're very process intensive, if you've ever done any deep reinforcement learning. Okay, so here's the architecture of the Eat, No Eat app. Essentially on top of it is a nutritionist model that sort of learns to categorize the food images. And it learns using transfer learning, so based on an established image recognition model, to using regression to pull out the protein, carbs, fat, and health. And I'll get into that here in a little bit. And then it sort of feeds that into, so it'll pull the nutritionist model will look at the image, extract those values that it's been trained to extract based on the food images it's been trained on. And then those 3 inputs are fed into a DQN agent, and that sort of tracks the diet of the individual. that's of the foods. So, you know, obviously chocolate cake is sort of on the high extreme of the one end that your foods you might want to stay away from. So it would be no wheat, for instance, or whatever. Okay. And the output of the model is a simple eat or no eat. And I'll get to the reason why it wasn't just stopped right at the nutritionist and then just output eat or no eat. That would essentially be my diet now. But the reason why I added the reinforcement learning piece to this is to sort of be able to track differences of food and be able to even sort of track problems in your diet or changes in your diet. Your diet will change over time. I mean, you might need to adapt your diet over time, different foods, different sort of foods that you might want to eat. You know, we're all eating more vegetables, for instance, you know, all staying away from more meats and stuff like that. So your diet will change over time. Okay, so the source code for this whole presentation is up on my GitHub's site. There's two repositories. There's the Eat No Eat repository, and you want to take a look at the reinforcement learning side. I have another side with a slide here for, it's called Practical Reinforcement Learning with Unity. It just shows a simple example of Q learning that you can pull down and play with. Okay, so the data preparation, and I won't break away from this slide, but the data preparation, there's a number of foods data sets that I essentially tried to use. I started off with the foods 1 million data set that was just too big to do any practical training on. And then I looked at a foods 101, which is 101,000 images of 1,000 images in 101 food categories. What I ultimately decided on was this smaller user recipe 5K data set, which was developed at the University of Barcelona. Can't remember the gentleman's name now. But it's essentially 5,000 images of food in 101 categories. And I wanted to keep this somewhat simple and manageable so you weren't training a lot of time. Okay, so essentially training the nutritionist was pulling in the food images, which were sort of classified. The original model was classified by food category. What I wanted to do was to take those food categories and relabel them and retrain the model so that it would output not just the food category, but a regression of the macronutrients of that food, or sort of an arbitrary food macronutrients. So what I based on this particular model were essentially the amount of protein, the fats and carbs, and sort of a health rating. A lot of foods, for me anyways, I can't eat a lot of salt, so that would be sort of a lower down the health rating, but it might have a lot of protein, for instance, so it would be higher in the protein scale. I'll show you all this. So the other part is I wanted to build it off an established application that was already developed. So what I used was an Inception ResNet version 2 convolutional neural network, one that's been trained on classification of the ImageNet data set. The ImageNet data set is about 2 million images of 1,000 classes. And this model was originally trained on that. So what I've done is I've taken that model, stripped off the layers, sort of stripped off the classification layer, and remade it for regression. And also what I've done is I sort of let half that model get retrained, and I'll go through that. So I'll show you this in a second, so that it outputs just the 3 values that I want, that are sort of based on this first number being the amount of protein from a value from 1 to 10, the second number being fats and carbs from 1 to 10, and the last one just being a health value. And these are just arbitrary values that just assigned to each food category. I mean, they could be improved on it, and you know, the number of these values could be added to as well. Okay, so building the nutritionist. This includes all these pieces. So essentially what I've done is I built this on 6 or 7 collab notebooks and pieces to sort of you know, break down the pieces that need to be trained. So this first one was here, the data prep, which is essentially also embedded in this. So I'll just go through them together. Not a lot of stuff to import as far as imports. The first piece was just using the TensorFlow's utility to pull down that data set that I've got hosted on a Dropbox, which is recipes 5K, processing that data, and then dropping it in all the images into the various folders. Now in this case, there's, I think, 50 images or 5, well, whatever. So each of the folders here listed in this list has a number of images based on the category of food. And then from there, I just imported some progress stuff just for displaying progress bars and stuff like that. And then what I've done here is I've tried out two different base convolutional applications for doing the transfer learning. One was a NAS, the other one was Inception. So when you're doing different transfer learning scenarios, you have to sort of set the data size that you're pushing into. So for the Inception one, it's 299. The NAS mobile was 224. So I decided to go with this sort of larger one, but what you're seeing here is I have to do a reshaping of the images. So when I load the images, this is essentially what this does. It just reload the images, resizes the images based on the image size, and then pre-processes the image based on the application. So in this case, NAS, or in this case, Inception. And this Inception is just cross for all the Inception models. And then what I imported was the food categories themselves, what I sort of classified for each food category. So steak, for instance, might be 9 protein, 1 carbs, 6 or 7 or 8 health, for instance, right? And then from that, process all that data together into this nutrient array is sort of just a way of relabeling the data. So you can see apple pie has values of 4, 5, and 4, baby back ribs. So these numbers here, the reason why they're showing like -4, 5, and -4 is because they've been normalized to, they were originally values from 1 to 10, but I've renormalized them to around 0. So they're from -5 to +5, essentially. So you can see, like, for instance, beef carpaccio, 5, -4, and 3. Just remember to add 5 to all these values, and you'll get what the food category is labeled as. So that just goes in to load the images. All those images get relabeled. And then based on that, get fed into the Nutritionist model, which is loaded here. So you can see here, there's the NASNet mobile, or the Inception ResNet. So this is the Inception model with residual networks. I won't get into too much of that. You'll see the input shape is that input shape which was set earlier. For the NAS, it's 224. For this, it's 299. And you can see the weights I'm using here is for ImageNet, and the include top false means I'm not including the classification layer. And this top is kind of it's a little backwards, because originally in neural networks, we often sort of drew them upside down to what we drew them now. And I'll even show you this when I look at the summary of the model itself. But so normally the top layer is essentially the output layer when we sort of look at some of these models, at least for TensorFlow, the way they sort of term it. So essentially what I'm doing is not taking that top layer. I'm not taking the classification layer. I'm going to put my own layer on top of that. And you can see here, this is just some basic tensor manipulations. So setting data through tensor slices, batching the data, and then you can see here where I'm building the model. And what I've done here is I'm just adding, okay, I'm not adding it here. So this is the base model. This is the base model, the base Inception ResNet model. And what it has, this is the input layer, you can see is 299 by 3 channels. And it has, I think this is about 800 layers in it. So you can see as I scroll through, it's got quite a few layers. And I'm still scrolling. I'll just scroll in a bit. Yeah, so it's got about 800 layers. So I'm using that, but then I'm attaching my own sort of prediction layer, which is going to be just a dense with those 3 outputs, right? So this is that dense with 3 outputs. That's going to be my regression outputs that determine the amount of nutrients or the level of nutrients that come out of a particular food category. And then that gets trained. We combine it all in a sequential model, and then I can do another summary. You can see that the Inception ResNet model has about 54 million parameters, and my dense layer on top of that has about 4,600. What I've done is essentially I've gone back through the model, and I've set about half of the model to be retrainable. The reason I've done that is so that I leave the top there's sort of the bottom half of the model, or you could think of the top half of the model as not trainable, meaning I want it to still maintain the same sort of feature weight or the feature sets it was extracting. So the top convolutional layers will essentially still extract the same features it was trained to extract as part of the image net. The thing I'm tuning here is the sort of the bottom half of the model by allowing it to train the bottom half, so it's increasing the parameters here to 30 million. If I just trained my bottom layer or my regression layer, that doesn't work too bad, but it doesn't get really good results. So what I found was just sort of through trial and errors that I had to pull sort of half this model apart. And this seemed to be sort of a good fit here around this sort of halfway mark of the model. It depends on what sort of features you want to extract. This isn't ideal. I'll get into some problems I have with some data types as well. I'll show later. So then this is just sort of going through attaching to the Google Drive. So what I can do is just set up a checkpoint, and as the model trains, it'll essentially save itself, save a copy of the weights to the Google Drive so that they can be used later. And you can see here down here that we're getting an accuracy of about 82%, which isn't too bad, and it works out quite well. I won't show you the other ones, and I'll get into some of these other things here. So yeah, so that's just building the Nutritionist using transfer learning to take that base inception ResNet model and retrain it essentially. Okay, so then what I did was, I won't show the collab notebook for here, but then what I did was I fed a number of images. So what I didn't do was essentially build up a test and training set, because what I wanted to do is just to make sure the model would work on just raw images. So I didn't want to sort of to do the same thing for a couple of reasons, mainly because if I was to set aside essentially a testing or validation set, I would have been cutting into a fair number of images off a smaller image set anyway. So what I decided to use was just upload a bunch of images and train them or test them raw against the model. And you can see here, this is a image of ramen that I'm testing, and you can see here that the model's giving me a 6 or 7 for protein, 3 for carbs, and 7 for health. I think the reason why it's giving such a high protein rating is you can see this sort of piece of meat in the egg here and what the color maybe looks like for other pieces. So what I found is by training a nutritionist model that can extract features is that I could throw other images at it that can actually often pick up newer foods or different combinations of foods and predict these values pretty spot on for the most part. There's a couple foods that are problematic, and I'll get to that, but for the most part, it's quite interesting. It essentially pulls out the proper features and gives you those ratings appropriately for whatever they should be. Okay, so now I'm just going to go into the reinforcement learning section. So there's just a basic introductory piece to reinforcement learning. Reinforcement learning is a type of learning we do in which we have an environment that is described by states of the environment, and inside that environment we might be able to do actions, and when we do certain actions, that environment might give us certain rewards based on those actions. So you can think of this as, you're playing a video game, you need to make a certain number of actions to make it to the end of the video game. Well, that's your reward. Those actions that you made throughout that sort of game were the actions that you made, and then each state of the game that you looked at, or each screen of the game, or each sort of piece of the game you looked at would have been a state of the environment that you've seen. Okay, so let's look at this a little closer. So RL really is all about trajectory optimization. Okay, and it's easy to see when it's applied to games. So here's an example of reinforcement learning environment that we often train deep reinforcement learning agents on. This is a lunar lander. This is an old 70s arcade game that I used to play way back when. But it's also pretty fun to play or use to train deep reinforcement learning algorithms on. So what we're looking at here is the lander is being controlled by a deep reinforcement learning agent that takes the state of the lander through each point, and as it's moving through, it sets the actions of these different thrust vectors on it. So on the sides or from the bottom. Those are the actions it's applying. And each of the states that's getting fed into the agent are its position in, or where it is positioned relative to the landing pad, essentially. Okay. We often commonly refer to as reinforcement learning as the credit assignment problem, essentially what actions you have to take to sort of maximize your credit or your potential profits. Another thing you often hear is tempo credit assignment problem, where you're starting to think of these actions in terms of time. Essentially, it really is, what are the actions I can make to maximize the reward? Okay, so when we apply reinforced learning to food intake, for instance, we have a person here that might be doing 3 forms of diet. So in the top form, they might be eating cupcakes, pancakes, and cake. And they might gain 5 pounds. And in this case, we'd sort of feed back to the agent that's sort of saying that we should eat these foods a negative reward, because that's not essentially what we want. So we want to sort of negatively say to the agent that these aren't the foods I should be eating, right? So these could be foods that you're eating on a regular basis that either are gaining weight or maybe causing you other health issues. I've had a person I was talking to about this app recently, where they talked about using it for other health problems like IBS or allergies or other problems like that. So in my case, I got into a case where I was just eating strictly protein, where I was still losing weight, but my health really went to pot. Anyways, and then the bottom one is just more to sort of the balance of foods that you eat long term, where you can still lose weight, but then also be healthy, is where we're using the reinforcement learning agent. Okay, so RL comes in many flavors. There's Q-learning, there's, you'll hear SARSA, DQ networks, various policy gradient methods, actor critic, there's all these different things and more. What I decided with is just to keep things simple. So what I used was Q-learning. So this example is back to that earlier code example I showed, which is the practical reinforcement learning with Unity. If you pull that down, open it up in Unity, one of the scenes show this model here. Essentially what you're looking at is various Q-learning agents trying to map their way through from this box, this green box, all the way down, or sort of the bluish box all the way down to the green box. This is the target. And you can see as they're moving through, they update their Q values. You can see this Q value is being updated as the agents walk across as to the optimum path they should be taking. So they essentially learn by updating their Q values on which path. It's the same sort of thing we're doing with training the DQ agent for ingesting food images. Okay, so in my work, what I wanted to do is sort of look at the optimum or best DQN agent that I could sort of use that was quick to train. So what I looked at, and you can look at here, is in the Eat No Eat repository, there's a DQN optimized. I won't go into this example right now, but it can solve the cart pull problem. If you're familiar with that problem, it's one of the first sort of deep reinforcement learning problems we throw at people. And it often can take maybe 1,000 to 5,000 iterations for most models that you'll throw at it. What I wanted is an agent that could sort of learn that very quickly. So through a bit of trial and error and some other work, what I've been able to do is sort of solve the cart pull in 35 iterations. And the cart pull uses a 40 box input. So essentially a vector of 4 inputs get fed into the agent, and then it only has 2 discrete actions, okay? So you can see here, here's the training curves. This is the training curve and the amount of reward it's getting. And you can see it's, as it goes up, it quickly goes on, when it reaches 35 iterations, it quickly, it's getting maximal reward. The maximum reward, I think, in this environment is 200. So it's able to solve in about 35 iterations, which was perfect for the problem I was looking at. Okay, so training the DQN agent. So here's the agent. So again, what we're doing here is we're setting up the images that are getting loaded. I'm creating this. The first is the model. So this is the transfer learning model. This is what I've broken it out into here. This is the whole code for loading the transfer learning model that we developed earlier, essentially the Nutritionist. And then down here, this is loading the images. What we're doing here is creating the model. And you can see this is the model, again, the same model. In this case, it's not trainable because we're already using a trained model, and we're going to sort of fill in the parameters itself. So it's saying the trainable parameters are 54 million, meaning all of them. But in this case, we're just loading it from the pre-trained or from that pre-run collab notebook. So in this case, just loading the models from the latest checkpoint of the models that were run on the last example. So here in the building the Nutritionist. So when they all get saved in the checkpoints, I'm just loading the latest checkpoint from here. Okay, and then from there, I can go through and run through the images, and based on training the agent can determine if it's eat or no eat based on the DQN. Oh, I think I'm missing some code here. Let me just go. Okay. I'm just going to quickly go through here and show you the DQN code itself. So this is the cart poll. This is the video playing from, let me just run this. This is just, it's failing almost immediately when it sort of does some random moves. And this is the training piece of that. And then this is the agent piece here itself. So this is the DQN network, or DQN. This is the part where it's building the model. So in this model, it's just using a dense 24 inputs, and then passing that through to a second layer. So in many other deep reinforcement learning problems, you can either feed it in raw inputs. In this case, we're just feeding in a vector of 3 inputs from the Nutritionist. But it could take image inputs as well, or it could take full image inputs where you'd have a convolutional model on top of that. That usually takes a lot more training, and I'll get into that in a bit. And then this is the action piece, and then essentially the experience replay is where it saves up the actions and moves it's made, and then it replays them to sort of feedback onto the network. I won't get into this too much. I'll just quickly go through this code, and then there's the training the agent. You can see here it's stopping. In this case, it stopped at 37 iterations. Okay, let me just go back to the presentation. So in the training of the model, what I did was just showed it foods and give it simple rewards of +1 or -1, +1 or -1, based on the food that was either eat or no eat. So the training is quite simple. I didn't deviate from the rewards. I didn't put sort of foods in order of anything. So in a practical real world example, for instance, you might have a certain number of foods that you might eat during a day. You might eat your heavier foods in the morning, lighter foods in the afternoon, and then a lot lighter foods in the evening, for instance. That would be sort of one thing that you want to be able to train your agent to. So you might do daily rewards or weekly rewards, for instance, or even rewards after each food. That's some of the things that I need to play with and sort of manage or understand. Okay, so, and then in the agent itself, what I did was to set up a different way of training so that the rewards could be expanded on so that it'd either be plus 10 or -10, and then trained over the trajectory. So essentially the foods that you fed it or you looked at, the order of the foods mattered, so that if you were eating cake and then protein foods, the cake might even be just a minor incident, for instance, or it depends on when you're issuing those rewards. So that's a piece that I'm sort of still playing with here, but can give you some ideas. So I'm not going to look at this here yet. I'm going to look at the last piece in this section. So the full app uses the webcam or device camera, works on a desktop or mobile. And it really only gives you the action of no eat or eat. And it doesn't really account for any training yet, but it could. I mean, it could very well easily. So the full app, what I've done is I put the full app, most of the source code up on the Eat No Eat. So in Collab, if I was to run this, I won't because it's already set up just to sort of the way I like it. But if I was to run this, it would pull down the source for the Eat No Eat app, change the directory to it, and then run the various code pieces. So each of the code pieces have been broken up. The first piece is just sort of mounting the drive. The second piece is to just import the DQN agent and train it. So this is just doing some preliminary training, or essentially bootstrap training of the DQN agent to sort of set it up. And I do that so that the agent sort of pre-trained a little bit on certain foods and the classes of foods, but it's done randomly for the foods. So the trajectory or sort of the order of the foods doesn't matter in that particular case. And that would be sort of one of the things you'd have to train into the agent after when you're using the app. And then this is the Nutritionist, where it's creating the model, and then it's loading the weights from the Nutritionist. So Nutritionist, again, is that transfer learned inception ResNet model. It's been pulled. Again, that's 54 million parameters. In this case, we're just doing looking at observing an image of the apple pie. You can see it's giving me some good results here. So low protein, high fat and carbs, and lower health. And then the app itself uses the webcam, so it just loads up the webcam, which you can do in Collab. And from here, I can show it foods off the webcam, and it can say eat or no eat. In this case, I've held up a piece of bread, so it's saying no eat, but the lighting conditions and some other things play into this. So, I mean, the accuracy of the model was only about 82%, so it could be improved on, and there's some other ways of improving on that as well. Okay, so, and then let me just get back to a nutritionist. So the reason why I wanted to use a nutritionist was to reduce the image state to some known constraints so that I could sort of identify the foods a lot more cleanly than not understanding how the agent was sort of identifying the foods. It was also a lot faster to train with transfer learning and using an established model. It required fewer training images to sort of get me the accuracy values I was looking at. Okay, here's an example of, normally you could have a DQN agent that's using a convolutional input. So it could be using a raw image input, feeding it into a convolutional network, and then giving you the action. So I could have built the app this way, but that would also mean that the feedback from all of these actions would also need to be pushed back, not only through this network part, which is essentially the DQN network that we looked at earlier, which was just a small 24 neurons in that one layer and 24 neurons in the second layer, and then an output of two neurons to give it the eat or no eat. Instead of that, they would have had to train all the other weights as well, which would mean that in order to do that, consistently and with good accuracy, you need a lot of images to train. So in typical deep reinforcement learning problems that taking visual input, the type of the games that they're playing with Atari, where you're just feeding the whole screen. So on those types of games, you're feeding the whole screen into the agent, and the agent learns to play the game based on just this as its state input. Okay, but those games can typically take from anywhere of 20 to 60 million iterations to solve, which, is not practical from just a single person. So that's why I use the Nutritionist to break that down, and also the DQN model to give it sort of lighter training times and could arrive at solutions faster, at least from a sort of a proof of concept app perspective. Okay. And then the future of Eat No Eat would really be adding more attributes as user input. So the other nice thing with keeping the Nutritionist separate is that you could add other user inputs or external attributes to the model. So right now it's just the 3 inputs from the Nutritionist getting fed into the DQN, or the reinforcement learning agent. but you could add things like age, weight, gender, activity levels, for instance, or maybe other attributes about the user, as well as external attributes like time of day, weather, other things, for instance. And those could play into factors of how to drive the eat or no eat. Okay. Also, it probably would make more sense to add multiple users, but then you get into the situation where, you're feeding cake to a younger user like a child who would really benefit from the cake from an energy standpoint, would probably feel good. So in this case, the app recommended no eat to the child. The child might say, well, I don't feel good, I didn't eat enough, has a negative reward, is maybe lethargic. Whereas, it doesn't eat the food, it's not feeling good. And then if it eats the food, you'd have to give it a -1 reward because essentially she feels good from eating the food. So you need to punish the app appropriately. But on the opposite side, we have an older user who eats the cake, feels bad, but has to give the agent a +1 reward because you're not feeling well. Maybe you get a sugar high or other issues with your health from eating too much carbohydrates or too many sugars, too much fat or whatever. Whereas if the app is recommending no eat and they feel good, you'd also give it a +1 reward. So you get into these sort of situations where it's a little tricky to think about how this works for different users from different perspective of foods and how you want to train them on those foods. And then, so the thing I sort of suggested earlier were the problems of the app. So I can eat fried chicken with no issue, but fried chicken often categorizes as high carb and high fats. And I just could not get the nutritionist not to sort of give it that high middle value number. It would always give a low protein value. I'm thinking it's because it also has foods like donuts and other foods that sort of maybe resemble the same in the images and maybe can't identify the shapes or whatever. So in order to improve the app, I need to sort of look at other ways of being able to identify foods like fried chicken or foods that could be, might sort of balance on being fried foods but still beneficial to somebody or being able to be eaten by somebody. So one of those fixes might be using self-attention with convolution. I sort of brought this up before in some other talks. Using self-attention to sort of be able to globally isolate the features in an image and be able to discern those features better. So what you can see here is that through multi-level attention maps, we can discern the outline of an image or other things. It's worked well in a lot of different examples, this type of using this self-learning attention with convolution. Here's an example with a residual network. It's using this. I haven't tried that. There's nothing really out of the box yet. I might sort of play with that a little later, but that would sort of take a fair bit of trial and error. But that was one sort of fixes to looking at using the self-intention mechanism with the network to sort of be able to identify those minor features you might see in foods. Okay, and then I just also wanted to talk about the dangers. The dangers from using an app like this and the dangers from promoting an app like this is a radical diet can really affect a person's health, can be extremely dangerous. Well, I know, for example, even though I was under doctor supervision, just eating the wrong foods can get you into trouble. Establishing rewards, which I sort of talked about earlier, can be a little difficult sometimes. There's a number of factors to consider. Do you base your rewards on just strictly weight loss? You want to combine health in there, activity levels, or overall sense of wellness, for instance. And then the other thing is that you often get people, they may not tell you the truth, or, for a number of reasons, they may give you incorrect foods, or the image may look different, or different colorizations, or a number of different factors. So there's a whole bunch of caveats there. But what I wanted to think about also was extending the concept. So being able to sort of track other activities for individuals, be it exercise, for instance, or training, being able to track maybe what activities you're doing over a period of time that got you to certain good point in training for maybe a marathon or other event or other exercise training, or even sort of helping students learn. I mean, you could think of this as instead of classifying foods with images, it could be a natural language processing model that classifies documents by reading level or academic content or other factors in the documents that you then feed to its student. And then that student could progress the learning and then sort of learn or understand which documents next or which content next to learn. Okay, so, and then commercialization, thinking about commercializing the app, likely need to be other sort of gates or ways to check the images being fed to the app, such as, if the image being shown to the app is a food or not even a food, is it always the same food, or, there could be a ton of reasons for somebody trying to disrupt or hack the app for whatever reasons, especially if the app has multiple users. There could be data privacy concerns. And, other things to consider would be, do you make the app global so that it would be sort of all users around the globe using it? Or would you make it local, specific to certain areas of where foods are common to those areas, or other pieces of information might be common to those areas, for instance? Okay, so then I thought about extending the concept to other things like, applications like drilling, for instance, since it's the Untapped Energy meetup. So I've got a fair bit of experience doing geosteering, for instance. So one of the considerations was you might, for instance, if you were doing a geosteering a well, horizontally drilling a well, this is essentially the type of images you would see while you're geosteering a well. These sort of inputs could also be fed into a model that could be used to use reinforcement learning to say, oh, you missed the target, got a negative reward, you're on target, good, you've got a positive reward. It's sort of a way of optimizing the trajectory or checking up on your steering mechanism. I was just going to share an app concept I built. First is a physical model. I used to carry it around with these little mats and called it the Perceptron game. I've upgraded it to a Unity app. It's hosted on a website, a GitHub site right now. I've shared the link in the chat notes for everybody to go to and look at if they want to see. And essentially, it's sort of just the same way of modeling or looking at an individual perceptron that we use for deep learning. And in this case, we're looking at trying to classify 3 different images. So the first image here is 2 black pixels. The second image is mixed, 1 white, 1 black. And the bottom one is all white pixels. And you can see there's different labels for each. And as I click on an image, you can see it's pushing the inputs into the various input nodes of the perceptron. And then right now we have all the weights set to 0, but I can change the weight. So I could change the weight of the bias here. And this first one is the bias, or 1, which is always there. And essentially what happens is we modify the input node times the weight. That gets passed into this summation function, which happens for all 3 of these sort of multiplications. So we sum up everything. So right now it's 1 times 0.25, which gives us an output of 0.25. Our expected output is 0. The actual output is 0.25. The loss is 0.25. So that means we're not training very well for that. If I change images, you can see I'm still getting the same loss. So obviously a bias of 1 with 0.25 weight is not going to work. So I'll just change this back to 0. You can see as I click through, it changes the weights. So for instance, if I'm using this central one, I can test this and I can up this. So this increases. You can see my loss is now 0.25. My expected is 0.5. And I increase this, and you can see now when I've updated this to 0.5 for this image, it's classifying correctly, right? Because the output is 0.5 and the expected is 0.5. Again, this is the input times the weight, and then all 3 of these values are summed up. The activation function that we're using in this perceptron is just a linear activation function, which means essentially just passing this raw value straight through to the output. So what I put this up here just as a simple example for you guys to play with and try and train the weights for all 3 images. So what you want to be able to do is train these weights for all 3 images so that the weights are going to be the same. So if I click for this image, it's giving me the correct labeled value. If I click for this image, it's giving me the correct labeled value. So this one's working. But if I click on this one, you can see my loss is 0.5, so it's not working with this image here.